Hello?
I think we cannot keep recording.
Oh, sorry. There we go. Should be good.
Yes, now we can.
Great.
Put the
All
link
right.
here. Put the link here where you are live streaming. We'll do it after it's ready.
Should be there.
There we go.
We made it. We're live. Let's go. All right. Great. I'm going to open up stream chat on my phone because I can't see it in both places for some reason. Okay. Let's hit it. Great. So, all right, we're here. Round 2. Polygon'z zkEVM. I think we got pretty far last time. But there's still a rabbit hole and a half left. So should we start with a recap of what we? I guess last time we started with the more with like an overview of how the system works. I mean, I would love to recap that quickly and just make sure that people get a brief reminder of the different components, and then we can dive into stuff.
Yeah, I can do the summary. The idea is that we have a node. We have a centralized sequencer. The sequencer sends transactions to on-chain, and then the critical part of the zkEVM is the prover. So once the transactions are on-chain, they are final. So anybody can process them. So anybody can compute the final state, but this state is not on-chain. It's not. So you need to put this on-chain, and you need to prove that this new state is valid. Okay. So all the point is here proving that given a state, given a set of transactions, the new state is correct. Okay. So we need to build a proof, zero knowledge proof that this state is valid. How we are building this proof in Polygon'z zkEVM? Mainly what we have is we're using Starks, and in the Starks we have a set of state machines. With these state machines, we build a processor, a specific zk processor, a processor. It's not it's very generic, okay, but with some specifics, but it's a generic processor. And on top of this processor, we are running a program. We call it the ROM, okay, but we call it the program that actually is emulating the EVM. So we just taking the transactions, processing these transactions, okay. And because this is running on top of these state machines, then we can generate the star, we can generate a proof that we are proving that the old state goes to the new state, okay. So the prover has like two big parts. One is the arithmetic part. We write that in PIL. Mainly is a set of polynomials, and so this processor, these state machines, we convert to a set of polynomials, and a set of relationships between these polynomials, set of identities of this polynomial. We write that in PIL, okay. And the processor is written in assembly. We have a specific language, this assembly, that we will today maybe we can see a little bit more in detail. And then we wrote the code that actually implements Ethereum. So if you want, maybe we can focus a little bit in this assembly. Well, as you want, but we can focus a little bit in the assembly language, and then we can go to how we are implementing all the Ethereum, all the Ethereum logic in with this language.
Yeah. So that makes. All right. So to recap, you have this processor that you have built. You implement the EVM or as close as possible to the EVM on top of that in this zk assembly, and that lets you both run it and just to check, are you running this processor in when you're actually executing transactions for users, is it the same code path for both execution and proving?
We do that. This is so it's not really necessary, but we do that in order to guarantee that we have exactly the same rules, that we have the same consensus, so that we simulate. So even the simulation of when you are calling something to the node, to equivalent to the get, we are calling exactly the same piece of code, so that you cannot go to a different state with the same transactions. This is just to reduce the risk of having diversity of, that maybe you process the thing in, if you have two programs that do the same, one program can do something different, and this is problematic. So at least in this first version, we are keeping to exactly the same version. So you mainly run this when you're generating the proof, okay? But also when you are, for example, executing an Ethereum transaction, a view of a transaction, so a transaction that does not mine, just a query. We're also running this code, and when you are simulating, when you are doing some estimate gas, for example, or when you are
really, you're also doing it there. That's interesting.
Exactly.
I guess
so we are doing it everywhere. Yeah, we keep simple and we keep the same. We had to optimize a lot this code because it's a code that's called many, and we are still working in optimizing that. But it's it starts being quite fast. There is still margin to improve, but yeah, that's an important goal.
Got it. Okay. All right. I mean, let's. Why don't we just start taking a look at it? And I'm curious. I'd like to look at the processor first, and then take a look at how the EVM is implemented on top of that.
Yeah, I can. Let me just share. Just
perfect.
Let me share the screen.
And I'll give the chat the right to also ask questions, and I'll bug you about it if they do.
Sure.
But we'll see. It's early in the morning for people, so I think they're tired.
Well, depending on the place of the world.
That's true. That's true.
Some people is going to sleep at this point.
That's also kind of early. Maybe it depends on what time they're going to bed.
Okay, let me just put this thing here. Let me share the screen. You see, enter screen. Let's see here. Processor. Let's see the processor. Good way to start is this processor. Okay, so this is the processor. I want to show you also a little bit the code of the executor. So at the end of the processor is a set of instructions, and you are executing a set of instructions. You have a set of registers. So here you have a set of registers, and then you have instructions that actually you are processing what you are doing with these registers. Okay, you can do additions, multiplications, move the registers from one side to the other, so you have a full assembly here.
And did you guys design all of this? You built the whole processor?
Yes. Build all the process. We have been working with this for a year and a half right now.
Were you working on this before you started on the zkEVM stuff, or was this?
Well, we were doing the Hermes one, which is payments only roll-up. Okay, I've been also, building the Circom and doing a lot of things in the zero knowledge, but in the last year has been focused on building the zkEVM, and it's a full engineering. It's a complex engineering system. It's with a lot of pieces. It's something that I would say that. It cannot be done by a single person. This is a team effort of many people just working in different parts. And here, all these, people. The team, we have people that's like expert in the arithmetization. We call it hardware. It's not hardware, but you are designing processors, so it's it's
Yeah,
good
kinda
similarity,
is.
you know. Just yeah. So and then we have the people that's writing the ROM. There is people that's writing the test. There's people that's writing the note. You know, there's we have different people working. You know, there's people that's working in the optimizations part. There is people that's working in the tooling. So it's you know, it's a lot of pieces. People working in the more in the cryptographic part, on the Starks. So it's a lot of people and you know, a lot of pieces and a lot of people working in the same in the same, you know, in the same project just to achieve the you know, full of code compatible zkEVM. So the processor, if you see how we are executing the processor, let me just share the code here. Let's see if I have something. Yeah, maybe just so let me just show the code here. Just close here. Just this is the JavaScript version. It's a prototype, but the C version is quite the same. Okay, but here we have all the state machines. And here in the main state machine, you go to the main state machine, and you go to main exec. Okay, and here mainly, well, what we have here is at the end is we have here is just this is the step. So this is a loop that's executing one instruction after the other. Okay, and well, this is what it's doing. You know, it's just for example, in this case, it's just computing the OP register, depending if it's in A, in B, in C, just computing the new OP, the OP register. Okay, and while it's doing the operations, and at the end is putting the registers, the result back to the OP. And here is just inserting what's everything. But this is I would say the slow version of this processor because it's interpreted. But actually, and this is what we're using for debugging, and this is what we're using for debugging and so on. And then we have like the C version, which is the fast version of this processor that's executing that. Actually, in order to go fast, what we are doing is this program, so this ROM, this assembly, we compile it. So we just have we compile this ROM in a Intel, so in a C. So we compile this we convert this program of the ROM to a C program, so that goes really fast. This is what we are optimizing.
Oh, and what is it written?
At the end is
in JavaScript.
See. Well, JavaScript is mainly for prototyping. Yeah, so JavaScript is what I write. You know, I'm just doing shitty code to prototype.
JavaScript is the greatest language of all time.
It's
well, maybe TypeScript.
No, it's the worst language. You mean that?
No. TypeScript is truly, without a doubt, TypeScript is the greatest language of all time, and I will die on that hill.
TypeScript. Let's say that TypeScript improves it a little bit, JavaScript, but it's not. I tell you, it's the worst language. But it's fast. You know, the thing is that if you are prototyping, and you know, I've been. You know, for many reasons, I've been developing a lot in JavaScript. JavaScript looks like a simple language, but it's probably the most complex language in the world. It's asynchronous and so on. So it's not the best language. Probably this would be much better to do it in Python or other. But this is
George
just
Hotz said it was
for
a good
prototyping.
language. George Hotz said it was a good language, yeah. So that means it must be. Well,
in any case, this is just for prototyping, and this is just for playing around and to going fast and to see that generating test vectors, generating constant variables. It's interpreted, so you can. It's easy to just to work, but at the end, when you want to do serious code, you need to go to Rust or C++. In our case, we're going to C++, and this is like the production code, if you want. And the node is written in Golang. So all the node is
okay. So it's
Golang,
and then what it calls into the C to run the state transition, and then spits it back out.
Well, yeah, we just take the ROM. The ROM is written in if you see the ROM, it's written in. Let me just here. well, we can go here maybe to the ROM is rated in assembly, in this special assembly. It's an assembly that we designed it. Let me just go to the zkEVM. So you see, just take, for example, this is the main, this is where everything starts. Okay, so this is the first instruction that's executed. Okay, and yeah, this is the assembly. So this assembly is compiled. Okay, at the end, this is converted to a set of polynomials. We have an intermediary JSON of this, so that can be read better for many programs. But at the end, this is converted to this compiled to a what would be equivalent to the machine code, but this is the polynomials. It's a set of polynomials where each row is an instruction. It's a set of polynomials where you have like different. Each instruction is a set of flags, and then each row has each instruction, and this is what we call the program. And this is a constant. It's a set of constant polynomials in the pill. That's what represents the program. Okay. And all the program starts here. Okay, so the program starts in here. But this is comments. Okay, you have included, but this everything starts here. So the first instruction, you see, it's the first instruction is this. But this is entry point. Okay, but this is not the last. It's not the Carlos. This is not the last. This is the yeah. This is the main. Yeah. Okay. Yeah, I can switch maybe to develop. That's I'm just.
I mean, it's pretty crazy. You're implementing the entire EVM in this custom assembly language to run.
Yeah, exactly. That's fun.
It's pretty crazy.
That's fun. It's crazy, but it's not. I mean, it's complex because the EVM is complex and there are a lot of details. But this EVM is not as big as you may think. Okay, it's not the smallest processor, but at the end is limited set of instructions. So,
sure, yeah.
So it's not it's a lot of work, but it's not like well, it's doable. You know, it's and here just and the cool thing here, and this is probably the most important thing, is that in order to test this code, mainly what we are using is all the test suite, all the Ethereum test suite. So we are running all the test vectors of Ethereum and checking that everything works exactly the same way that Ethereum does. Okay, so here is the where we're starting the code. The first is we are putting the step. The step is the state trace, so the clock number. You know, the first time the first line you execute is the number 1, the second is number 2, and 3, 4, and it's incrementing. So we are just putting the step to A, okay, and we are checking that is 0. Okay, so that's just this is a check that we are starting from the beginning. That's not a jump or something crazy in the middle. Okay. Some of the registers, so all the inputs of this program. So this program have some inputs, okay, and all these inputs are in the registers at the beginning, and mainly are the hashes. Okay, so here we have the alt state root hash. We have the accumulated input hash. The accumulated input hash is so when you are inserting transactions, it's a kind of a blockchain. So when you are inserting transactions, you are you are accumulating. So so in each batch you have a set of transactions that you need to execute. That's mainly what you are doing is you hash the alt accumulated hash and all the transactions. Okay, but you just the data, and then the alt accumulated hash and the transactions, the alt accumulated hash and the transactions, and you are just creating this chain of hashes. So this allows us to go, for example, from batch 24 to batch 35. Okay, so and we go from one accumulated hash to another accumulated hash. It's like the concept of a block hash. Okay, but it's with this idea of accumulating all the previous transactions. Okay, so here is where
quick question. Do you have the concept of? Do you have multiple? Do you have the concept of blocks, and do you have multiple transactions per block, or is it like?
Well, Here internally, so internally we have the concept of batch. We always talk about batch mainly to distinguish between the layer one block. Actually, we could call it block, but we prefer to call to batch to a layer two block. Okay, so that's just a naming. It's just a naming issue, but it's convenient for non-mixing concepts. Okay, but
Sure.
the idea of a batch would be a layer two block. Okay, but and in each block we can have many. So in each batch we can have many transactions, and the batch is the unit for. So the basic proof proves a batch, okay? And then we can aggregate proofs. We can aggregate the proofs of 10 consecutive batch or 20 consecutive batch or as many consecutive batches as we want. Okay. Here,
1 second, Jordi. I think it's worth mentioning that from the point of view of the L2 user, one transaction will always be one block. So we have the concept of batch for whenever we interact with L1 when we send the grouped transactions and for when proving. But if you would ask the JSON RPC and so, and the context of the transactions when they got executed, we have this mapping of one transaction, one block.
Sure, I mean that's the same as optimism today. So
exactly the same. I think that we were looking. I think we were looking also how the optimism and Arbitrum were doing that and other rollups, and we come up that I think this is the best way to approach if you want to have a fast finality from the central perspective. So it's just you can give you can close so you send a transaction, you can close a block. It would be kind of a virtual block, but it's a block that's equivalent to a transaction, and you don't care the number. But from the user perspective, it's okay. This is what's set at
I mean, this is necessary. Like the EVM, unfortunately, for the context of chat, the EVM does not have you don't have this concept of like intermediate state roots that you can give users as a confirmation. And so you really need to seal a block and give the user the full block. And so if you want to process a transaction, immediately seal it, give the user the confirmation back, you kind of have to either do one transaction per block, or I think Arbitrum made an interesting tweak recently with Nitro, where they produce one block. They essentially have like a time period, like a very short time
5 seconds, or exactly. This is exactly the same. So it's just maybe one transaction per block is a lot, especially if there is very crowded blockchain, and then you just say, okay, you close one block every 5 seconds, and then you put all the transactions that are in these 5 seconds. Great. Okay.
They do it even shorter. I think they do it at like half a second or something. It's very, very, very short.
Yeah, exactly. But that's even that. I think this is a good point, because then the block, you just remove the block overhead that you may have in the database and in the places there. So this makes a lot of yeah, it's exactly this. The block is, so the block that the user sees is quite a virtual block. Okay, it's
sure. Yeah, and I think people are kind of used to that by now at least with the way that Arbitrum and Optimism have done it. So
so at this point it's just one block, one transaction. The problem of joining many transactions to one block is then you need to keep track of which block you are, and then you need to put somehow that in the state. If you have one transaction, one block, then okay, it's deterministic. You don't need to decide where you split the block, and that's why it's okay. But from the layer 2, this is just the prover has no idea. So this is just a way. It's a view of the it's a view of the layer 2. It's not internally. It's just batches.
Right.
Okay.
And so, really quickly, what is the syntax here of this zkEVM? So you have these two. Is the stuff on the right? Is that?
Yeah,
there's just comments, or those actual? I'm
well, no. This is comments is
semicolons.
Column. column is, so here we have the column splits like this. Every line has two parts, left side and right side. Okay, the left side, mainly what we are saying is what happened with the registers. Okay, so in general it's going to be an arrow. Okay, and then the best is just go here. Okay, and then the idea is here is you have registers, and in the left arrow is which registers you select. Okay, so in general this is going to be, for example, B, register C, register SP, register gas. Okay, and you can, in the left side you can have additions. Okay, so maybe you can want to add A and B. Okay, or you can A times 4 and B times 5. Okay, you can do a linear combination here. Okay, and you just select them. Also, you can put a constant value. So the instruction is for an immediate value. So here, for example, you are putting a 0 here. Okay, and the other thing is that you can put in the left side is the free input. Okay, so everything that you see $1 in the left side, so everything that's $1 here, that means that's you can put. There's an instruction that allows you to put any value there. Okay, so and this is we call it a free input. It's like the executor can put any value there, but actually, in general, because you put the value and then later on you check this value. Okay, for example, this global exit route, you put here the global exit route, and then you store here, and then later on you check that the global exit route that you computed is actually this one. Okay, but you can put whatever you want. When you see $1, is you can put here, and this instruction you can put whatever you want, because you are going to check later. For example, you want to do a division, you put the result in the division, and later on you check that you check with a multiplication that the result of the division is okay. Okay, so this is the thing. Okay, sometimes
just to confirm this, for example, this the arrow at the top. This is you're selecting register A, so you're operating on register A now. Is this the idea, or what is this step?
Step is a register. Actually, it's kind of it's a very special register, but it's a register that was returned in. So how many clocks your program has executed already? Okay, so in here it should return a 0 because the first. But if I call the register here, it would be 1, 2, 3. It's going to be a 4. Okay, and every time that you put a clock, every time that you execute instruction, this register just increments by 1.
Oh, I see. Okay, so you're loading step into register A. Then you're putting 0 on. You're putting 0 there. And then
you're putting 0 in the OP. Okay, and then you have assert. Okay, that assert just checks that what's in A and in the OP is equal. Okay, here we have some. Here maybe Carlos, you want to share the presentation of the maybe just check some of the instructions that we have. Okay, because this instruction is the assert, for example, checks that A and the OP are equal. OP is the register that you select. What's going in here. Okay, so here you're just getting the B value. Maybe just want to share.
Yeah, let me share my screen, then I will just comment on all the instructions that we have, and later on, I think it would be easy to check the code. Okay, so for example, can you see my screen?
Yeah.
Yes.
Okay,
just put some easy. Just to start, put some easy transaction, some easy instruction. Just put an at or something that's easy, or the asset, for example. You see that. Go to the asset.
Yeah,
the asset, for example, you see that.
The third one is what John said. I mean, it compares what you have in register app with what you have in the op, which is the intermediate value.
You can go, for example, to the arithmetic instruction.
Yeah.
But here at, for example, at is you see that, for example, you are just checking that A plus B equals up. I don't know, this is not well set here, but you are checking that A plus B equals up. Okay, that's what you are checking in the app. In the arithmetic, you are checking that A times B plus C is equal to D times 2 to the 256 plus up. Okay, so you are checking this operation. So with this operation, you can do any 256 bits operation in the EVM. Okay, so this is the instruction. And if you go, maybe go to some instruction in the right side, so then you have the arrow. So in the left side, you just which registers you want to put in the OP, or you compute the OP, and the right arrow is the assignment. So if you want to set, if you want to put the result of the OP to the register A, then you put an A. But you can have, for example, you can put A, B, C. For example, 0 arrow A, B, C means that putting a 0 to the register A, to register B, to register C. Okay, so it allows you to copy
at the same time.
Exactly, yeah, because it allows this state machine, this processor allows to do these crazy things. You know, it's a little bit different of a normal processor, but it's an assembly. And then after the column, then we have the operation that we are checking, so that we are executing or checking. And in the free input, when you have a dollar, when you have a single dollar without the instructions of what you want to put in this free input, then that means that's implicit. So then the executor just checks what instructions you have, and then it does it accordingly. For example, if you are doing a memory read, then it will put the value that's in that position in the memory. If you are doing an addition, then it will put the result of the addition. If you are putting a storage read, then it will take the value of the storage and put it there. So if you see a dollar in the left side and you don't see anything, that means that's implicitly, by the context, you can know what's actually doing here. Okay, so this is, and the language is very much that. Okay, so you have a set of instructions, you have this left, right, and this is the operator. Here you have jumps. Okay, so you can have jumps, conditional jumps. You have also arithmetic operations.
Really quickly, just to confirm. So this is when you're looking at these instructions here, and you say, you know, the assertion A equals OP. This is literally register A. Can you do assertions on other registers, or when you're doing assertions, do you have to put the value into register A?
In this case, you have to put the value to register A.
Okay.
All the instructions, also most of the instructions, they use the OP as one of the parts. For example, the assertion, one side is the OP, okay, but the others are fixed, okay. So in this case, is you need to know that assert goes to A, so you need to put something to A, and then you do the assert.
Okay, sure.
Assert in this case means it means that you cannot compute the proof. So assert in general is when it's like a catastrophic error. It's just you cannot really compute the proof. This is assert. This is not for checking edge cases. It's for actually something went wrong. Okay, so something is, for example, if you put a division, if you are doing a division, and you need to check that the multiplication is okay, but if it's not okay, then it will be an assert. That means that the proof, you will not, so the proof stops. So the proof will not be valid. It's something that's ensured in the same proof. If you want to check an edge case, something that may happen, then you need to do some check and then do some conditional jump and actually do it accordingly.
Okay.
One important thing, one important thing here is that so the prover, given a set of transactions and a set of transactions, I would say, given a string of data, so don't matter what it is. So any string of data, as far as limited, you can always prove what's the result of executing this piece of data. If this piece of data are the well-formed and valid transactions, then the state will evolve.
Mm-hmm.
If these transactions include something that is wrong, maybe something random data, or just something wrong in the RLP, or something that's wrong in the invalid signature, or for example a nonce that's not correct, or then the state, it's also evolves, but it keeps the same. It's just an operation. It traces an operation, but you can prove that. The important part is that no matter what information you put as an input,
sure,
the system will be able to move forward. So to test. So it will be able to So it deterministically have a new state, no matter what's the data. The only thing that we require is that the size of the data is limited, but we check that by the smart contract. So this is not we warranty that in the smart contract. And this is good because, for example, this allows for example, to have the what we call it the forced transactions. No, forced transactions are transactions that the user can send. So are L2 transactions that a user sends to L1. And these forced transactions means that the sequencer is forced to include those transactions at some point. Okay, so if they don't include at some point, then the sequencer will just not be able to put more batches. So they are forced to put these transactions, and these transactions are whatever the user wants. In general, this is going to be exits in general, but it can be any L2 transaction there. Okay, and so with this we can prove that these transactions are executed accordingly to the state of layer 2. And this is important because this is what why the system is censorship resistant, at least until a certain point. Full censorship resistant means that the user would be able to use the layer 2 as any other user, but at least the sequencer, centralized sequencer, cannot lock the funds, or of course not steal the funds, but they cannot even lock the funds into the system. They cannot lock your funds.
Yep, makes sense.
Okay. Do you want to maybe you want to go to the little bit to the ROM and see a little bit how it's organized?
Let's do it.
Yeah, maybe Carlos, you can continue here. You can explain a little bit the pieces. And
okay. So basically, what we're doing is to process a batch, as Jordi said. No? So what are the different paths of processing a batch? So the different paths are basically at the very end, we are loading the register, is what Jordi was showing the code. Later on, we are just forwarding the exit route from layer 1 to layer 2. Exit route is the route that has the bridge in order to perform the process that has been done in layer 1. Later on, they will claim all the assets that they lock in layer 1 and layer 2. Later on, what we are doing is processing all the transactions. We're processing the RLP of the transactions. Later on, we're processing the transactions, and at the very end, we are just doing all what we call all the batch computations, all the batch assess. So basically, this last step is assuring that the data that you have introduced to the ROM is correct. It matches with the one in the smart contract. I think in the following slide, you can see it better. So at the very end, it's just a sequencer, just putting some data transactions into the smart contract, which is basically the data availability. The smart contract call is called sequence batches. And how does it look like, this data availability? Okay. We are using here a specific encoding regarding the transactions, and basically the transactions is composed with the LLP of the transaction parameters, nonce, gas price, gas unit, blah, blah, blah. And we just concatenate the signature at the very end. Okay, this is the encoding of the transactions, and later on, this encoding will be decoded in the ROM. Okay, we will see how to do it. And you need to decode this correctly. Otherwise, if it's incorrect, then you can finish the batch, but the transactions will not be processed. Okay, and which other data do we need to assure that you put correctly in the batch? So basically, this is the computation of the accumulated input hash that I explained at the beginning, and it contains the alt accumulated input hash because it's like a chain. The batch hash data, which is basically the hash of all the transactions altogether concatenated. The global exit route, which is the route of the bridge. Of course, timestamp and message sender. Message sender would be basically the receiver of the fees that will be accumulated in layer 2, the codebase. Okay, so basically we have this kind of inputs, then we process the batch, and we have some outputs. I mean, the most common one is like I have out-of-state route, I have some transactions, I process the transactions, and I have the new state route. But besides that, we also have the accumulated input hash, the batch number, we have the local exit route, which is the bridge route in layer 2 that we forward to layer 1 in order to be able to forward assets, the asset of tokens from layer 1. And of course, we have the chain ID as well. Okay, so now we're going to see the snippets of code of the ROM. So, and this one is basically what Jordi shows, okay? But with some syntax highlighted, which I think is a little bit better. And as you see here, as Jordi mentioned at the very beginning, we are just asserting that the first step that you run into the ROM is the step 0. And basically here we are just loading all these inputs into memory. Okay, that's what we are doing here. The second step that we do in the zkEVM is we are, as I mentioned, we forward the exit route from layer 1 to layer 2. And at the very end, we are just setting a storage position in a specific smart contract in layer 2, which is the bridge in layer 2. You need the exit route in layer 1 to go to layer 2 in order to perform the claim. Okay, and this piece of code, what it does is basically add this value, this global exit route, into the smart contract, the bridge in layer 2. Okay, and basically it computes the mapping storage position and inserts the data. And it computes the storage position by hashing the position of the mapping in the smart contract, which is 0, or it could be whatever, but in our case it's 0, and the smart contract address, obviously. And then this storage position, in this storage position, we set the value using the instruction of the sstore, which is basically adding a leaf into the state route that we use, into the method here. Okay, afterwards, what we need to do is, okay, so the data that the sequencer put in the smart contract, which is the data availability, it should be an Ethereum transaction. Okay, so let's check it. So what we're doing here basically is just decoding that data. We are interpreting that data. So is this data, in case of the LLP code decoding, LLP code decoding, we are just checking if it's a list, and later on we are reading the values. We are reading the nonce, we are reading the gas price, we are reading the gas limits, and so on. Okay, and here the values must be, I would say, must be correct. So I cannot have a nonce that is larger than 64 bits. Otherwise, the encoding of the transaction is not good. Okay, so I need to have all of the parameters, even if they are 0. I need to have, at the very end, I need to have the signature. Okay, and I need to read all these parameters correctly. Okay, so the data availability must follow this LLP encoding.
Sure.
Okay.
Can you show me the where you jump if it's invalid?
Which one?
The invalid TX RLP tag.
Here. Yes. I think it's not here. So what happens in that case if we have some random data, we could say. Oh, sorry. So what happens if we have some random data that a sequencer adds into the smart contract? It means that this random data, it's not an Ethereum transaction, or it cannot be processed. So what we do basically is to stop the processing of the ELP data. Then we will not process any data, any transactions, because it's not valid, and then we'll finish the batch. And well, basically, this piece of code here, what it does is it finishes the loop of the ELP transactions, and it jumps to the last step of the batch processing.
Okay.
Okay, so
Got it.
here, basically, we are not processing any transactions because the data is not what we expect, so we cannot process that data.
But we are proving that the data is wrong. We are proving that the data is wrong. Yeah, that's important.
Yeah.
So the program executes well.
Right. We are proving that we are passing exactly the same data that has been put into the smart contract.
Right. Yes. Okay. That makes sense.
Because basically, and this happens in the last step, at the very end of the batch, we are assuring that this new accumulate input hash is exactly the same as the one that the smart contract computed. So here, and then we are assuring that the data that you put during the verification process is indeed the same in the smart contract. Otherwise, the hash will not match, so the proof will be invalid.
Right.
I will just jump to this piece of code, and at the very end, it's just this piece of code that I'm highlighting. Basically, we are just creating a new hash. We are just putting some data into this hash, and then we digest this hash. Okay, and the result of this hash is the output of the batch, and this output should be exactly the same as the one that we compute in the smart contract, which is, let me check, here. So this is the new accumulate input hash, which is the kickback of the available packet of the all accumulated input hash, all the transaction hashes together, the global exclude the time standard transaction. And we are doing exactly the same in the raw. But of course, it's a different language, so it looks a little bit different. But at the very end, it's just what I show at the very beginning, just this hash here. So we basically have been seeing this hash computed in the smart contract and in the raw. I mean, it looks a little bit different, but at the very end, it must match. Otherwise, you cannot perform a balancing. But what happens if the LLP is correct? Okay, what happens if the sequencer just puts some data over there that it's indeed an Ethereum transaction? So here, what we're going to see now is how we process this Ethereum transaction. As Jordi mentioned also, this Ethereum transaction may or could not be made processable. I mean, and it depends. I mean, we need to perform some checks at the very beginning. We need to perform what is it called in the paper, the intrinsic checks. We need to check that the signature is okay. We need to check that the chain ID of the transaction is okay. We need to check that the nonce also matches. We need to check that the sender has enough funds in order to pay the initial value of the transaction. But those are the initial checks that we are doing. If any of those checks are not fulfilled, then the transaction could not be processed. Exactly the same as Ethereum. I mean, if a get node receives a transaction that has a different launch from some senders, so the transaction is just rejected. So here it happens the same. But what happens if the transactions also fulfills all these checks? So we are basically we are going to process the transactions. We are going to increase the nodes of the sender, and we are just going to start reading the bytecode of the smart contract, and we are going to process that. Okay, and so for example, here I will just show super basic of code in order just to see an example. And I will show a very easy one, which is basically the addition. Here, there are some, the prover has some resources. Well, let me just, I think it's better now. The prover has some limited resources, and we need to check that we not get waste of these resources. We don't waste all of these resources. This, I would say, it's like the gas for the zkEVM. Okay, and here we are just checking that we are not running out of this register. But the rest of the code, you will see that is probably the same as the Ethereum does. So we check the stack. If we have enough stack values in order to read and perform the opcode. We check if we have enough gas in order to perform the opcode. If these two restrictions are fulfilled, then what we are doing, we are just reading two values from the stack, and then we are performing an addition. Okay, as we saw before in the instruction of the add, it takes register A and B, and we are storing the result of this instruction. It is saved in the intermediate register of, and then we save this into the stack again. So we are reading, we are just popping two values from the stack, and we are just inserting one value to the stack. We are pushing one value to the stack. It's what the opcode of the add does in Ethereum. So we are doing exactly the same. And if you check on the rest of the opcodes, we're basically doing the same as Ethereum. You can check all the arithmetic, blocks, context, crypto, CSH3 is over there. Less than, later than, segment less than. And you will see very similarities with the ones in Ethereum. So I would say it's easy to read the code once you get a little bit familiar.
Yes, Carlos, go to the add one. I want to explain important things here. Just go to the add. Here you see this instruction. This instruction actually it has like two operations in the same line. That means that so this assembly allows, so depending on the instructions, they can be run simultaneously. So actually what's doing this? Let me explain this because it's interesting. Okay, so the dollar means that's a free input. We can put whatever we want because there is an add. Okay, so and the add means that with A plus B must be equal to the OP. Then this dollar means that in the frame we are putting the result of A plus B. Okay, and this is going to go to the OP, but we are not storing this anywhere. Why? Because first we are checking that with that we are checking that this result is valid. So is the addition of A and B, and then the result of A we also call this M store. So we are storing that on the stack. So that's why there is no output in the registers. So we are doing at the same time. We are doing here in this instruction. We are doing at the same time. We're putting a free input, which is the result AB. It's a free input because implicitly this takes add, and then this result of app is stored in the store, and then the SP++. So here the stack pointer is a special register that allows you to increment or decrement also in the same instruction. So mainly with one single instruction we can do mainly a full addition. Of course, here is just to load the variables to the registers from the stack. Stack is part of the memory, so stack at the end is a stack pointer. It's just part of the memory, as explained. Okay, and the first one are just checks in the gas, in the Ethereum gas, and check of the counters. Okay, this is a very easy instruction, but it's quite clear because this is the pattern of everything. Okay, the mole is very much the same, but instead of using add, is using arithmetic, the arithmetic operation. Actually, here I think that we are doing a call. Okay, so we have internally we have these calls A call mainly is just it's a jump, but setting the return pointer to a specific value. Okay? And because multiplications, we are doing a lot of multiplications. We have like a kind of a procedure just for doing this arithmetic. But the idea is exactly the same. Okay. Subtraction. So with this, most of the opcodes are quite trivial. Less than, greater than. They are just using this arithmetic state machine. Of course, if you go to opcodes, maybe you can go to some more complex. If you go, for example, to create to, or you go to return, or you want to, there are some opcodes that are a little bit more complex to execute, or bull mod, okay, or there you need each opcode has its own logic and intrinsic, but at the end it's just programming what the opcode does.
Exactly. So, for example, in the create, you need to save some variables. You need to save the memory offset, the memory size, in order to create the smart contract afterwards. You need to copy this bytecode. You need to read the memory and hash it in order to create afterwards the address when you deploy the contract in the create. You need to change the context because you are creating you are increasing the depth on Ethereum, for example. I mean, it's more tricky, we could say. Also,
the percentage, when you see the percentage sign, just for the syntax, the percentage sign, this is just a constant. Okay, so this is just a it's just a value. Okay, but instead of putting the value there, we have a file of constants, and then we just change there. But just define. It's in C would be a define, just a constant, a fixed value. Okay, so it's just an alias of a number. Okay, so just okay. Here, memory. Well, Carlos already explained it a little bit, but the memory, we have this idea of context. We have one single memory, but actually this memory is divided by context. Okay, so each context, so each call has its own. So it's like if we have many memories. Okay, every time that we do that one smart contract calls to another smart contract, then we open a new context, and then you have a free memory where you can work. And this memory has the memory, which is the memory of the smart contract memory by itself, the stack. Okay, because when you are calling a smart contract, you reset the stack, so you have like a new stack, and then you have variables that these are system variables. So there are variables that are specific to this context. For example, which smart contract called this, or the gas that's allowed, or everything that. So all the information, all the variables used by the ROM that are specific to this context itself. I think that after the stack is very small piece. So after the stack, we, for example, we put all the call data, and yeah, so that's the thing. For returns, for example, we sometimes do cross context copies, because you need to pass data from one side to the other. Yeah, and we have all the important part here is how we hash. I don't know if you want to go to that, but inside we can do all this hashing. At the end, it's just the idea is that we can. So a way to understand a hash is like a read-only memory, if you want. Okay, so you can have a string that can be variable length string. Okay, and then this has an address. Each string has an address, and then to this address you can read three things. So you can check three things actually. Data, so data at some position, you want to check, for example, that at position 3 there is a 24 or something like that, or you can put until 32 bytes. You can get a window and check that this data matches with this hash. You can check the length, and you can check the digest, the actual hash of the data. You can do that in Ketchup or in Polygon.
Well, so this is my selfish optimism thing, but I have a so we have this desire for a simple zk proof given a subset of some input. So given a pre-image to a hash and the hash, the pre-image to the hash is, let's say, too large to be included on chain, but we want to prove that some subset, some substring is included in some larger preimage. Is this what?
Yeah.
Sort of the
No, we actually in some state machine, in one state machine, in the hash state machine is going to be the full string, okay? Because we are using here linear hashes, okay? And then you are just like reading, so you are just reading some part of this state machine. But in the one state machine, you need to have everything. For your case, here it's interesting to mention that Blake 3 has this, so that they compute the hash as a Merkleization. It has a Merkleization. So a hash of a string is a Merkleization, and then things like what you are thinking, just check that part. You can just check that part of the hash is a hash. Then it's easier to achieve. You can also build with a Merkle tree by itself, but it's a little bit less efficient depending what you want to do. In our case, at this point, we are just loading the full program or loading.
So you've loaded the full thing. It's just reading. It's reading from a specific.
Yeah,
index.
exactly.
Okay. Cool. Let's see. I feel like we're kind of getting there. What's the most interesting opcode implementation in your opinion, or EVM opcode implementation?
Mulmod, maybe that's an interesting
okay.
one. Yeah, that's
Mulmod,
a nice one.
It was a tricky one. It was implemented by Jesus, in fact. It's very well documented, I would say. But it's very tricky. It's very tricky because you're doing a multiplication that could overflow until 512 bits, and you need to take care of, I would say, a lot of things. Okay, this is the Mulmod. Well, in fact, we built a utility named utilmod because we are going to use this utility for the pre-compiled of the Xmod. But basically, the Mulmod is coded there. But I mean, this Mulmod that does not just only involve EVM comprehension, but also you need to be very aware of the mathematics that it happens over there in order to check that everything goes fine. So I will try to explain it, but it's kind of tricky, I would say. So here it's basically all the explanation. So at the very end, how do you prove that modular argumentization is okay, basically? So here, basically.
One sec. By the way,
yeah.
someone on the stream says it's a little hard to hear you. Is there? I don't know if that's just a mic issue. If it's just a mic issue, whatever, then we can. Doesn't matter.
The mic issue. I had it yesterday, so.
All right, whatever. Well, the stream's gonna have to deal with it then. Whatever. Sorry, stream.
Okay. So basically, you need to compute the integer part of the modular operation and then the result of the modular operation, and then you can check it with the highest part rather than 2 to 256 plus the result, and then you can check that the operation was done fine. Okay, this is basically these two lines of comments over here. Okay, but the tricky part here is like the integral part could be higher than 2 to 256. So we need to compute, we need to be sure that, again, this number could be divided into the lowest part and the highest part. So we prove, again, that this integral part, we compute it correctly. because we are just working with the registers with 256 bits, basically. Okay.
I see. Okay, so you have to break it up into multiple operations.
Yes.
Yeah.
I mean, it's this one is a little bit tricky. I mean, you need to read it twice or three times, and write it in a paper, and then understand what is going on behind.
Yeah, there is a full paper explaining this whole mode, but yeah, the idea is that you do you just check three multiplications on a set of numbers and a range check and then the remainder is lower than n or something like that, and then you can guarantee mathematically that the result is valid. Okay? But actually, the interesting thing is that it's not that you are computing. When you are computing, the executive is computing by hand some values in there. Okay. Here, what we need to do is validate that this is actually the right value. So it's just we are checking that the things are valid. So this processor is not about computing things; it's about checking things. Actually, you put whatever you want. This is done in the executor, and then you check that the result is okay.
Sure.
This is maybe here I just put one of the most complex itself. Complex in mathematical terms. There are others that are more in the logic. For example, the create2. Create2 is some code call. It's or call or delegate call or those are important, so are difficult ones. And then there are some of the opcodes that rely in another state machine. For example, storage is very easy in the language, so in the main state machine, but actually there is a full state machine that deals with all the tree and all the specifics of the sparse Merkle tree that we are using. But from the ROM perspective, from this program, you just do memory storage read and storage write, so which is quite easy. Okay. Well, there are details, for example, the last weeks, for example, we dealt with the touched address. The Ethereum has very specific things on depending. It's not the same an address that has been used and it's empty, or then never used address is a touched address idea. The gas depends on what you did. So there is a lot of, I would say, small details that the EVM has. Okay. And the cool thing is that with this language, we can fine tune, so we can adjust very much to do exactly what Ethereum does. I think that right now we are very close to run the 100% of all the tests. I think that we are missing like 40 or something like that. We are working on that, but it's 48. Okay, so it's just but we are working on that, and let's see if we can finish or just we pass all the tests. So 48 out of 13,000 and more, right? So it's just a lot of tests that are already passing.
Yeah, that's impressive.
Here. But still, it's just it's work. It's still, that we are in more edge cases and very explicit things on that.
Cool.
Here, for example, the details is that, first of all, we just implemented the pre-EIP 155. Okay, this is very convenient. For example, if you want to deploy Gnosis chain, or if you want to these smart contracts that have the same address in different chains. These are using this pre-EIP method. You can do that also in Create2, but there is still a lot of apps that are using that. So this is one of the things that, for example, we implemented recently. But yeah, it's I think that at this point, this Carlos team that has been dealing with all the EVM, they must be one of the people that knows better the EVM, how it works, because it's a lot of small details. So what happened when there is an underflow on the stack, or what happened if there is a lot of exchange cases that you need to take a look, simulate, read the yellow paper, fully understand how it works.
We are hitting ourselves to the wall once again, reading IPs of what happened, and finally you got the error, and oh shit, okay, there is one IP that thinks that maybe you can attack Ethereum with 3 billion, so you cannot send a transaction from a smart contract. So we need to check that because there is an Ethereum perspective that is failing. For example, this is just an example. For a super weird, not I would say not weird, but an IP that I don't know at least. So yeah.
Yeah. Are you gonna implement the I guess you have to, the Ethereum object format stuff? That'll be that'll be fun when it comes
Then,
to
which object? The Patricia trees?
No, the smart contract object format EIP, the one that the smart contracts can't start with the 0xEF prefix, and then they're eventually gonna have like code sections and data sections in smart contracts.
At this point, no. If you want me, now I was before implementing the zkEVM, I was very fan of extending the AVM, and at this point, I tell you that please don't touch anything. Stop doing. Stop doing. Let stay. No, and actually, I think is every time I think that's better to simplify. So EVM, I think it should be more. The changes that should be more in simplification terms than in the ampliation terms. But this is I tell you after implementing the EVM itself, I think it's still it's a little bit complex and probably could be a little bit simplest. Of course, the EVM has a lot of history and. It was, it's Ethereum started. This was implemented in 2014 or 2015, and since there, a lot of things happened in Ethereum. But for me, I'm more for simplifying, stabilizing, and simplifying the EVM more than in extending. And so on. So when I see a new EP of a new extension of the EVM at this point, I'm no, please, no more.
The Ethereum object format is interesting because it's kind of like an extension for the sake of simplifying, in the sense that they want to. You can kind of use imagine it like smart contract versions. So you could say that there's like version 0 smart contracts are the smart contracts that we know, but then you could have a version 1 smart contract where you block the use of the self-destruct opcode, right? And so you can kind of like have a simplified EVM where, let's say you have it's a little annoying if you want to be fully equivalent, but you could have a version of the EVM where you only allow version 1 smart contracts, and now people can't deploy self-destruct, and you don't even have to bother implementing it because you're never going to execute it. So you could have a simplified version of the EVM because you only support specific contract versions. And certain contracts may not work, but not many people use self-destruct in new smart contracts, so it's not really that big of a deal. That sort of thing. You can simplify the behavior of certain opcodes yeah.
That's definitively interesting. But again, the thing is maintaining how many versions of the EVM you want to maintain, and complicating the clients at the end is. I'm not sure. I'm not a client, so I'm not sure if it's a good idea. But it's interesting. So I think it's interesting, these proposals, and they have some motivations and interesting. But at least if you ask me. After implementing and seeing all the details and the small details and edge cases and things that already has, for me, I'm more. So I like the IPs that's I don't know. There is one, for example, for simplifying the gas calculations or something and just putting a simple formula. That's great. Things that simplifies. So
sure.
I
think it's okay. The gas schedule. It's ridiculous at this point. That's a separate. That's a nuisance. Well, so okay. Someone in the chat asked, you know, are you just going to follow every EIP? Essentially, is the question. Are you just going to deal with it, or is there a certain point where you would say, I'm not
Look,
implementing this?
here the idea is try to, well, we'll see in the future. So right now we are implementing what it is, what is currently in development. Here probably, and here is a matter of governance. So I hope that at some point Ethereum is frozen, and I think this is a little bit the idea. So at some point Ethereum is going to be finished, and means that the EVM should be frozen, and then it's a perfect time for rollups to also froze the implementation of that. So probably this is still a long run, where we are talking about, I don't know, 2, 3, 4 years, 5, I don't know. But at some point, once Ethereum is, you know, all the Serenity, you know, all the sharding is done and somehow, and it's like mission completion, and the Ethereum
15 years from now.
Yeah, well, I don't know, but this is interesting, because of course it may change the milestones in the world. But if you read the Ethereum white paper, if you go to the 2014 and you see the different steps, actually the idea of what should be Ethereum is still in there. Okay, maybe we change the names and Ethereum 2, and there are a lot of tagging that change, but at the end is scalable, smart contract, blockchain, and we are going in that direction. What's going to happen, I don't know, but I think it's clear that at some point this is, so we will have a blockchain that's with EVM, and it's scalable and with sharding, and then maybe that's the moment to think in frozen the development and keeping stable, and pretty much like Bitcoin is right now. Somehow it's like just to stay stable. This is the final thing, and then it's the idea of rollups is a scale Ethereum. So at some point, rollups will also freeze on that. We're a little bit early in the stage, so we're gonna launch mainnet in the coming months. So we need to see how everything works, how this goes to production. There's a lot of unknowns still, and we are not gonna close. What we're gonna implement there, but at some point we'll have to think in freezing the development if you want to have a really decentralized system.
Yeah, that makes sense. Cool. Any final thoughts, final things you want to add? I know we're actually half an hour over, but so thank you for staying on. But if there's any, I don't know.
Well, just we are very close to froze the code for the first version. Let's see if we can do it in the coming weeks. We are gonna just we will announce probably much better than here, but we will the testnet. We were going to regenesis the testnet in 2-3 weeks at some point, because we're going to introduce all these aggregations, all the aggregation proofs in there. We are finishing all the auditors trainings, so training the auditors for auditing. So we are just trying to explain what we more or less explain to you, but explain to the auditors, so that the people can review the code, and we can start this phase of reviewing. And let's see if we can launch as soon as possible. That's what we are mainly focused on.
Sounds good. Cool. Well, thank you again. I think I have a much better idea of how all this works. It's very interesting, at least for Polygon'z side. Now we'll have to figure out what the other guys are doing.
It's a pleasure, man.
Very much appreciated. I'll make sure all this stuff goes on YouTube. And I'll probably keep diving into the code, and if there's anything else that doesn't make sense, I might hit you up for another session, and we can get into it.
Perfect.
Cool.
Sure, Kevin.
Cool. Thank you so much. Have a wonderful Tuesday, and see you on the internet.
See you around. Bye.
Bye bye. Thank you.
All right. Hello, stream. That's it for today. That was a lot of fun, though. All right, I feel like that's. I feel like I get it. We get it. Polygon, zkEVM. Maybe I need to do a recap at some point, but generally makes sense. It reminds me a lot, and I don't remember if I said this at the end of. I probably did, and so now it's just going to be the same outro. But it reminds me a lot of Arbitrum's AVM. And so I wonder if we're going to see the same pattern of what happened with like Optimism and Arbitrum happening eventually with Polygon. I'd probably put money on it that it will, just because it feels like history repeating itself. The AVM was interesting, right? The AVM was a special purpose virtual machine designed for the bisection game, right? So if you know about optimistic rollups, the fraud-proof game it's a back and forth game where you find a single instruction that you disagree on, and you execute that one single instruction. The AVM was a special built virtual machine so that you could do this back and forth game easily. And so they built this special purpose virtual machine, just like Polygon is building this special purpose zk processor. Same idea. They built their own assembly language, just like Polygon built the zkASM, right? And then they run their own assembly language on this custom virtual machine. And in that assembly language, they implemented the EVM. I mean, it's really close to a one-to-one mapping in the behavior of. I think Polygon seems to be much closer to the behavior of the EVM. I think the AVM had more significant differences than the EVM, but it worked, right? It was an interesting strategy, and it worked. And then eventually, Optimism, Arbitrum both realized that that instead of proving this custom virtual machine, you prove a general purpose virtual machine, right? A virtual machine that languages already target as a compiler target. And so for Arbitrum, that was WASM, WebAssembly, and for Optimism, that's MIPS. And so for both MIPS and WASM, basically the goal, the idea is that you can take Geth, right? You can take Golang, and you can compile it down into WASM, or you can compile it down into MIPS. You can run it. And the nice thing about that is that you don't need this custom assembly, right? You don't need to maintain this custom version of the EVM, right? Because you could see in that code that Polygon showed, there's a lot of complexity there in building a version of the EVM. The EVM is complex. There's a lot of edge cases. They said, I'm pretty amazed that they said that they had, what was it, 1,300 or 13,000? I don't know. That's a lot of tests. And then there's only 48 left. That's really impressive that 48 tests that they still need to pass. But I do suspect that the future is going to look a lot like, I think it's going to follow the same path as with optimistic rollups. I think that we're going to start seeing like a zk WASM. There's already RISC-0. I wrote a blog post about this a while ago, and I feel pretty strongly about this. I think what's going to happen is like you're going to have these Gen 1 zk rollups. They're all going to look like this, like what Polygon is doing. I need to talk to Scroll, but you're going to have these Gen 1 zk rollups, and then the next generation is going to be a zk MIPS or a zk WASM, and instead of running this custom EVM, they're just going to run Geth. Right? They're going to take Geth and they're going to compile Geth down, and they're just going to prove Geth. Or Aragon or whatever. And the nice thing about that is that you don't have to, you could see their Jordy, was when we started talking about like the Ethereum object format. Like it's annoying, right? All these EVM extensions are really annoying if you have to build, and you're hoping that the EVM is frozen. But if you're implementing, if your proof system doesn't care, and you don't need to maintain the EVM, it kind of becomes like less of a problem, right? So this is why the optimistic rollup teams don't care, but the ZK teams do. Anyway, my guess is this is the pathway we'll see in the future. It's just funny to see these parallels between the way that ZK rollups are being built and the way that optimistic rollups were built. And I would recommend to anyone building a ZK rollup today to look at the pathway that optimistic rollups took because I think they're much closer than people typically imagine. The proof is, you can almost think of the proof as an implementation detail, but currently the proof is so, it bleeds so much complexity into the rest of the system that it doesn't feel like an implementation detail right now, but I think one day it will. So that's my final note there for this session. It's funny, it's just interesting to see those parallels, and we'll see if there's another. I'm going to look at the code again. If there's anything else I don't understand, I'll probably try to get the team back on because it's always fun to have them here. Clearly know what they're doing. I mean, you got to know what you're doing if you're going to implement your own ZK processor, and then you're going to go and you're going to build the EVM on top of your own processor. I mean, that's impressive. It really is. So, congrats to the Polygon team. I think this is a very viable approach. Even if I don't think it's the long-term approach, I think it's a good approach for now. So, and thank you to all of you for coming through, showing up. Yes, very cool, very pog. That's right. That's it is really very cool. So, and so is the AVM. I gotta say, Arbitrum was equally impressive with the AVM, and just because, but I think also just because it was impressive doesn't mean it was the right long-term move, and they understood that, and they eventually scrapped it. But that's, what gets you here doesn't get you there, right? What got me here won't get me there. That's, I think this is probably the right move for now, and I highly suspect that there will be a Polygon'z zkEVM Part 2 in the future, V2. Cool. All right, I think that's it for today. I think next time I'm going to try to get Scroll on board, or maybe ZK Sync, maybe Risk Zero. We'll see. I'm already chatting with Scroll, or I was chatting with Scroll a couple weeks ago, so I'll hit them up. I think they're doing something very different. Well, not so different, but I don't think they're building this ZK processor system. I think they're proving the opcodes directly. So it'll be an interesting comparison. Cool. All right. Thanks everybody. I'm gonna go upload this to YouTube. Stay tuned for a link, and stay tuned for hopefully Scroll if I can get them. Bye everybody, and see you next time. Oops, here's my stream thing.